Hey everyone, myself Kaushik Ranade, and I am a graduate student working on AI safety and basically LLMs in general. And I'm a master's student and wrapping up my thesis this month. Uh, and today I'm going to present a paper which is less is more, hierarchically recursive reasoning in tiny models. So let me just share my screen real quick. Oh, sharing is not turned on. I might. Okay. Can I all see my screen?
Yes.
Perfect. Okay. Good morning, everyone. Today we are going to talk about this paper, which is Less is More, Recursive Reasoning with Tiny Networks. It was published by Mr. No, Alexia Martineau and by Samsung Sale Research. The key point, the audacious claim they make here is that a 7 million parameter model is beating 671 billion parameter model. Well, let's see how valid are their claims. So here's the roadmap of the presentation. We'll start with the problem itself, right? Like why LLMs struggle at puzzle tasks, which require sequential refinement. Then we'll take a quick recap of hierarchical reasoning models since Moj covered that topic, a couple of meetings ago. Uh, then we'll talk about the fix itself, the tiny recursive models, simpler, smaller, and better. Identify weaknesses of TRMs and how we can improve them using TRMs. And then we'll close with benchmark results and a few key takeaways. Lots of visuals, so stay with me. So, why do LLMs struggle at sequential refinement tasks or puzzles in this case? So, if you look at these numbers here, right? Now we're talking about this paper in retrospective. I'm pretty sure that the newer models have higher scores at Sudoku Extreme or other puzzles, but when the HRM paper or even the TRM paper talked about Sudoku, right? DeepSeek R1 and O3 Mini High had 0% on Sudoku Extreme dataset, which in itself is crazy because DeepSeek R1 has 671 billion parameters. The challenge itself is for LLMs is to generate everything token by token because of their autoregressive nature. The issue with that is in case of Sudoku, where each step of the solution, like for example, in Sudoku, we have numbers in the grid, right? Even one small error, in this case, incorrect prediction in a grid, can lead to entire sequence of steps to be invalidated. So what I mean to say is a single wrong token can completely invalidate the final answer. Now, in order to fix this, potentially, they use chain of thought. But the issue with that is it's expensive to run. It requires a lot of compute. Second thing is it requires high quality of reasoning traces, which are often hard to produce. And even after having uh, enough amount of compute and high quality of reasoning traces, the generated answer can still be wrong because we don't have an objective way to evaluate uh, the solution itself using value. Which could be which, but there's multiple reasons to that. One of them is we don't have access to high quality of value functions during the RL refinement step. Regardless of it, chain of thought helps, but it's still not enough. Now, for ARC-AGI 2 benchmark, in retrospective, the paper claims that Gemini 2.5 Pro had around 5% of test time. These numbers are talking about test time accuracy. So when they trained these models on ARC-AGI 2 benchmark and then run inference time tests, Gemini 2.5 Pro scored 5% accuracy is what they mean here. Now that's different in current times. Gemini 3.1, as last updated, has around 45% of test time accuracy. and Claude Opus 4.6 has around 69.2. So that's definitely an improvement, but the key takeaway here is that it took a lot of compute and a lot of high quality reasoning data and a lot of reinforcement learning shenanigans to get it to this level. But the authors claim that we don't need all that. We can just have a tiny network and run it recursively to beat, or not beat, but come somewhere around close to these numbers. Now let's take to the crux of the problem, right? Like why autoregressive generation fails. Autoregressive generation works as follows, right? We start with one token, and based on that, we predict the next tokens. So let's say in case of Sudoku, we predict the numbers 5, 2, 6, and then 7. If the next number we predict is incorrect, this error propagates throughout the sequential generation steps, and the whole answer is invalid. It's different. What's different with recursive refinement is that it fixes errors iteratively. So we start with one draft of the whole Sudoku grid, and then it starts doing predictions. If the predictions are incorrect, in the next draft, the predictions are slightly improved, and so on until we get the final Sudoku grid where the numbers are correct. Now, let's take a quick glance at hierarchical reasoning models. Remember the core motivation, right? Like LLM's outputs are not trustworthy. They generate tokens one at a time. And if they mess up early, everything downstream is wrong. Chain of thought helps, but it's expensive and needs good training data, and generated reasoning itself can be wrong. So what HRMs proposed was two small networks, inspired by how brain works, right? The Kahneman's system one and system two thinking, plus a deep supervision step, which improves the answer over multiple recursive reasoning steps. And the results were also impressive. They trained everything on a 27 million parameter model, which was effectively beating a 671 billion parameter LLM. Now let's take a quick look at HRM's architecture. So inspired by system one and system two thinking, as the system one or the FI runs at a high frequency of steps for input latents ZI, right? And then we have system two thinking, which runs at a less often frequency FH, having the input latents ZH. Now there's four learnable components here. We have input embeddings. Let me actually just put on a laser pointer because I'm having a hard time. That is not what I want. Yeah. Um,
Just one quick question while you are looking for the laser pointer, if I
yeah.
may. By frequency, what do you mean? Like the number of tokens per second or something like that? Like
No,
what?
by frequency, I mean how many times you're doing a forward pass through the network.
That is for a given sequence, or
Yeah,
how
you
do you
can
differ?
like let's say we define input token, right? Like the input here is of batch size, sequence length, and the embedding dimension.
Okay.
So we pass this tensor through system one, like in this case, 4 times.
Oh, the same embedding matrix you pass it 4 times, and then
Yeah, so like output of system one, I'll explain that. I'm coming
okay,
to that.
okay.
Anyways, but the whole point is that we pass the input 4 times through system one and only twice through system two. So this is less frequent and this is more frequent. Do you get that?
Okay.
Yeah. So that's what I mean by high frequency and low frequency. Anyways, so the four learnable components are input embeddings, the low network, the high network, and the output head itself, like to decode these embeddings back into understandable tokens, I guess.
Just sorry, one clarification. So in the diagram, you take the input, then pass it through system one, then get the output of system one, then pass it through system one again. Like, do you pass the output from one step into the input?
Yes, I'm
Is
coming
that
to that, Niravan.
okay? Okay, sorry,
Yes,
sorry.
yeah. No worries, no worries. It's okay.
Okay.
So each network, like system one and system two, is like a four-layer transformer that uses RMS norm. There is no bias and Swee glue activation function. So let me explain how the whole system works. So data flows in shape of, say, batch size, sequence length, comma, the embedding dimension. And then these two networks recurse over these embeddings. Uh, so let's say we pass the input embedding, right? And then it goes through system one. We get some output, and it does again pass through system one recursively 4 times. It's not the same input embedding, right? The output of system one is passed back to itself, and then it recurses 4 times, but not sequentially. So let's start. So we have our input here. It goes to system one. We get some output. Then it's passed through system one again. But also parallelly, we pass the same output to system two, right? Again, we get some output back from system one. We pass it back to system two sequentially along with system one. So effectively, we do 2 forward passes through system two and total of 4 forward passes through system one. That's what I meant by high frequency and low frequency updates. Are we clear till here?
Yep.
Okay. So now that we're clear with this, one thing to notice here is that all these steps are no-grad, and the only steps where we actually back propagate the errors is on the final 2 steps, uh, which get essentially back propagated through. Now they justify this using implicit function theorem, where they assume that after running it for 4 passes and 2 passes here, we basically converge at a fixed point. And if that's true, then we don't really need to back propagate all the errors. We can only back propagate errors at this step. Is what they assume. Uh, Moving on to the deep supervision. So here's where the magic actually happens. So deep supervision runs the whole forward pass 16 times. Each time the latent features from previous step initialize the next one. So what I meant in the last figure, right? So the output from this system one network will initialize the next recursion step in system one itself. Now, think of it like, okay, step one gives a rough answer. Step two starts from step one, where it left off, and then it sequentially improves it. By step 16, you're effectively reasoned it through, well, effectively 384 layers of computation, but you only back propagate through one step at a time, right? And I think the results speak for itself. HRMs are like pretty good compared to the state-of-the-art LLMs back then. Like for example, like O3 mini is accuracy on ARC-AGI back then was 34.5%, and HRMs were honestly beating them, which is quite great. So it is able to emulate a effective layer depth of 384, but requiring less compute compared to actually larger LLMs, right? So we understand that HRM work, but there are some catches to this architecture, which I'm going to explain in the subsequent slides. So the first issue is the fixed point assumption, right? They claim that using implicit function theorem, uh, uh, we can back propagate through the last 2 steps. Now this requires that the recursions actually converge at a fixed point. But here's the thing, HRM actually don't do fixed point iteration. They only do forward pass. And they assume that after 4 recursions, we are reaching convergence. There is no mathematical proof for this. They are making the empirical observation and then saying, okay, sure, we can do backpropagation after 4 recursive reasoning steps. But this is not a way to justify this fixed point assumption, right? The second issue is ACT. Oh, my bad. That is a color palette. Let me just remove that. Oops. Uh-oh. All right. That was my bad. Let me share the screen again. Is my screen visible, right?
Yeah.
Oh, thanks so much. Yeah, we'll ignore that. That never happened. Push. Anyways, so where was I? I was explaining ACT, right? So issue two, which I was talking about, was that ACT is actually expensive. ACT actually stands for Adaptive Computational Time, which is like a Q-learning objective where the network learns to halt the recursion steps in case it understands like, okay, I'm currently recursing on the solution, and I came across somewhat correct solution, so now I'll stop recursion. That is adaptive computational time. Uh, the issue with this is that a Q-learning loss, learning a Q-learning objective requires running an entire additional two forward passes. So all six evaluations run again. So every training step, we perform uh, two additional forward passes for reduce like learning the Q learning loss, right? So forward pass one, main recursion plus the halting loss itself. So we have six total function evaluations. And in the second forward pass, we continue loss for Q learning objective. So another six function evaluations. So each time you take a one forward step, you are essentially doing two forward passes, right? And this is not efficient. The second thing they talk about is in their paper is reliance on biological arguments, right? The whole Kahneman system one, system two thinking. They justified by saying that if both of these networks are running at different temporal frequencies, the resulting answer or the resulting solution must be better. The because brains like they're basically putting analogies with the brain experiments on mice, which is honestly a fascinating part of neuroscience, but it makes nearly impossible to do principled ablations. Like why two features and why not three, right? Like we can go beyond that. And biology, just because biology says so, right? There is no ablations in the original HRS paper. We're just left guessing that, okay, sure, it helps, but like why does it help, right? That's another issue with HRM's paper. Now let's talk about the fix, right? TRMs. So the core idea of actually before we start here, do any of us have questions here? Maybe so far.
I
Um,
have.
yeah. Go ahead,
Did
Nirmal.
someone else have a
Yeah,
question?
go ahead.
Aditya, you can ask first because I already. Yeah.
Okay. I was just asking the Q learning you said, right? So
Yeah.
what is that?
So so here, right, in this
Mm.
figure,
Mm-hmm.
they're performing recursion steps,
Yeah.
but they in their network they have a think of it like a parameter, right? They have this
Mm-hmm.
ACD parameter that
Yeah.
determines whether we have to stop this recursion process early
Mm-hmm.
or do we keep going.
Okay.
And this is a Q learning objective.
Okay.
Yeah.
Okay.
They learn whether to halt the recursion steps or not.
Okay. In the middle, once it is like reached.
Yeah, so it reaches after recursion, like is the
Mm.
output correct? And then it does the whole recursion step again, right?
Okay. Mm. Yeah. Got it. Thank you.
Of course. I think you have a
Yes.
question.
So the whole point of this recursion models, like as I understand, is to reduce computation, right? So, but like when we are doing the recursive passes,
Mm-hmm.
we again have to do those multiplications and softmaxes and all the attention steps in transformer calculations, right? Like
True.
uh, so uh, the so this the model itself will be smaller, like it will have small memory footprint in the GPUs, but then the number of computations will be equal to the number of parameters times the number of recursion steps, right? Like
Mm-hmm.
so.
Okay. So what you're saying is true, but when it comes to training, right?
mm,
So when we're training these models, what's expensive when we say something's expensive in a network, what we talk about is usually a forward pass, and
mm,
the computational step which is expensive is a backward pass, right? Like back propagation. But in this case, we are performing, say, three forward passes and only doing a back propagation for the last step, right? So in this way, we are not doing it at every recursive step. We are only doing it for the last recursion step. And that saves
Okay.
us computational
Okay.
resources.
Okay. So, in the forward pass, like in the backward pass, we save, except for like we only do backward pass one time, so we save for the other recursion steps. I'm just trying to understand the thesis. So, like, I don't have a big understanding of how the big networks work, but at a smaller level, like when we give some embedding matrix and then pass it through a transformer layer, then the output we get is a distribution over the entire vocabulary, right?
True.
Then if you take that distribution over the entire vocabulary and then pass it again, uh, the like how does it improve? Like, is it because like the output will have a better way of asking the same question, and then when we do it again and again, it somehow improves the prompt or something like that. Like, I'm just trying to understand what happens intuitively.
Right. So okay, let's start. Okay, that is a good question because it doesn't like this diagram really doesn't address the actual architecture of HRMs. To be fair, the point of this presentation was not to explain HRM, but I'll just do a quick refresher anyways. So, in just
Mm-hmm.
consider a normal language model, right? You have input embeddings and you have output embeddings, and
Mm-hmm.
the everything in the middle is where the processing happens. So in case of HRMs, you only have these transformer layers passing queries and keys and values, right?
Mm-hmm.
And each time we recurse, they are learning what. So what they are learning is, in case of Sudoku, I'm looking at this grid and what numbers do I need in order to maximize my objective function or minimize my loss, right? That's what they're learning essentially.
Mm-hmm.
And then in the last step, we perform the output embeddings. Like, do you understand now, like what I'm talking about?
Mm-hmm. Yeah.
Yeah. So
So
essentially, yeah.
so if I add on to this, just imagine an LSTM cell. It also has input latent coming into it, right? That input latent in the first step would be zeros because you don't have any knowledge about what's the sequence right now. But as you propagate through time, you will iteratively refine that input latent, and that would give you a better answer at the end, right? So that's how
Mm-hmm.
word classification used to be done. It was done in like long ago before transformers. You would
Hmm.
pass sequences, and the LSTM cell would recursively go through them and finally give you a classification out of that. So
Yeah.
it's something like that. So you have a input latent that's being iteratively refined with the first time you have given the input, and the latent gets refined over time.
Mhm.
Okay. 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 Okay.
Yeah. Yeah. So yeah, that's I would say that's a good analogy right now, but it's easy to get confused because this is like not a LSTM cell, right? Like we are
Yeah.
not actually storing any memory tokens or something. This is like just transformer layers and they're just improving on itself. But we can make that analogy here to some extent.
Yeah, because these latents also would be some form of like extra tokens that are added on top of your sequence, right?
Yeah,
That pass through the transformer layer. So these tokens are that what are getting refined over the
true.
passes.
Yeah.
Yeah, we
It's
could
like a
look at it like that. Yeah.
short-term storage. You can say that, yeah. But yeah,
Yeah.
that's just HRMs. Now
Yep.
let's talk about what's wrong with HRMs, right? Like there's always some area to improve. So there's three key improvements according to me, which I talked about, right?
Yeah.
Now let's talk about the fix. All right. So here's the core idea. Its pitch is quite simple. One tiny network instead of two. We still perform deep recursion, and we progressively refine its results. So there is no fixed point theorem. We simply backpropagate through full recursion, and we ignore the whole implicit function theorem entirely. There's just a single network. Instead of two medium networks, we have one tiny two-layer network, and we do one forward pass, simplified ACT, and well, where this whole system is now more optimized, right? The results are also really good. It's like around 87.4% on Sudoku compared with like 55% in case of HRMs with lesser amount of parameters. Like for TRMs, the parameter size was 5 million and HRMs it was 27 million. Now let's take a look at the architecture. So if you look at the bottom right, we have three inputs here. Input X, which is the question itself, the prediction model makes, and its latent reasoning, which we call Z, right? These get concatenated and fed to the network. The network itself is simple. We have self-attention, ad norm layers, and FFN. They haven't mentioned that in the paper, but it's a Swiglu activation function. So not just normal feed-forward network, it's a Swiglu feed-forward network. And here they are using RMS norm instead of layer norm. And they apply, there are two such layers and they recurse through it around 4 times, right? And once we concatenate these inputs and pass through the network, we perform recursion steps. So there's two kinds of recursions. There is one inner recursion and there's outer recursion. We run inner recursion steps for say 1 to n, where we update this reasoning step at every recursion pass. And after we perform n number of inner recursions, we just update one y prediction. And then we run this whole loop n+1 times to improve on this current prediction, right? So that's a deep supervision loop. So for step 1 to 16, say we update the z parameter, and then we do one final y prediction update. We calculate loss on y with respect to the true answer and detach the gradients for y and z, and then do the next step for 16 turns. And after we're done with this latent recursion, we go to one deep recursion step where we perform t-1 iteration. T is a hyperparameter without gradients. And then finally, for one gradient step, for the final iteration, we perform backpropagation. So it's sort of similar to HRMs, but here we are not making that fixed point assumption that sure after these many reasoning steps it will converge, and that's why we are doing. This is how they have defined their architecture, and we will perform one backpropagation step on deep supervision. Right. Now coming to the algorithm. We have these three functions which I mentioned. We have latent recursion, we have deep recursion, and the whole training loop. The latent recursion, we are doing it in range, like right, we have six inner recursion steps. Now this is another hyperparameter they have defined. You can have n equals 4 or 3, but the best results they got in the paper was by using the value of n equals 6. So they run this loop 6 times, update the value of z, and then get their one final prediction. That's latent recursion for you. And then this whole thing is run inside the deep recursion function, t-1 times. In this case, they have decided the value of 3 because that's the most optimal value according to their empirical observations. And we run this effectively 6 times 3, so 18 times, right? And then finally we get our prediction. And for the last recursion step, which is, I guess, for this, it will be the one index 1, we run a loss.backward. So that's the algorithm. I hope it makes sense.
Yes, it does.
All right. So let's what are the key insights from these two papers, right? So HRM has this low and high level architecture feature, right? But in case of TRMs, we only have one single hierarchy, but we have two different variables for it. So y is our current answer, right? What was ZH in the HRM paradigm? Now it is replaced by y. The lower level features, or ZI, is now, we call it latent reasoning. So effectively, we are performing high frequency updates here and low frequency updates here, without using two separate networks. Now here we don't need any biological justification. We just have our current reasoning and our prediction. Now, why exactly two features, you might ask? Like similar to why exactly two networks, why exactly two features? Without Z, model forgets how it got its current answer, right? Like Z acts as chain of thought. This is my current latent reasoning, and I need to improve it. Say without Y, model must store the answer inside Z, which is we are basically polluting its reasoning steps, right? So we store the current prediction in Y and its reasoning in Z. If we add more features, say Y, Z, and P, they tried doing these experiments. They tried adding multiple features, but what they came across was the accuracy was actually dropping. So it just makes sense to distribute the hierarchical features into two different latent variables. The next thing that we talked about was fixed point theorem, right? In TRMs, we don't need that because in HRM, say we were doing 4 recursions without gradient and 2 recursions with gradient. Because we made an assumption that we had reached to some convergence point and we can use one-step gradient approximation. The problem is we don't really know if we reach that point of convergence. With TRMs, we are specifically defining that for T minus 1 full recursions, we run it without gradient, but at the one last step, we run gradient and back propagate through the whole recursion process. So in this case, we don't need to make an assumption. We just run the whole backward pass through the recursion steps once. We're not skipping recursion. Sorry, we're not skipping back propagation through layers. The impact is quite visible, I would say. Uh, I'm sorry. Yeah. Anyways. So with one-step gradient approximation, which is HRM style, we have a significant disparity in the accuracy values, I guess. Now here's like a little infographic, right? Why 2 layers beat 4 layers? 4 layers in this case is like two different networks, right? So with only 1,000 training samples, so let me put it this way. More layers means more capacity, right? Like that's the old deep learning assumption, right? But it sort of backfired. For 4 layers with n equals 3, we had accuracy score of around 79%, but with just 2 layers, it improved it by, like 10%, right? There's 8% accuracy increase with half the amount of parameters. No, why? With only about 1,000 training samples, bigger models tend to overfit, and the recursion already provides like enormous effective depth. So we don't really need parameters. We just need a small network and perform deep recursion on a small amount of data. Now, there's a quick note. They have an optional swap. So for tasks which have limited context length, like in case of Sudoku, your grid is like 9 cross 9. So it's like almost 81 tokens. So it's not really like a long range dependency, sequential dependency task, right? It's a small task. So for that, you can replace the self-attention mechanism with normal MLP applied on the sequence dimension. It's like an MLP mixer, if you know what I mean. So on Sudoku tasks, specifically for small tasks, so which is Sudoku, MLP TRM with MLP architecture actually had an improvement of around 13%. So what Inside This gives us is like depending on the task, we can change the inner architecture of TRMs and get better results, right? The difference between Sudoku and ARC-AGI here is that ARC-AGI grids are somewhere around 30 cross 30, meaning it's around effectively 900 tokens. And now this is a huge task as compared to Sudoku. Coming to the simplified halting mechanism, in case of HRM, we had ACT, right? Where we are performing Q learning with 2 losses. We have one halting loss, which decides whether to halt at current recursion or not. And then we have a continue loss, which determines whether we continue from here or not. So this is 2 forward passes per step. But in case of TRM, we only have one single loss, a simple binary cross entropy, where we ask the question, has the model reached the correct answer yet? And we drop the continue loss entirely and perform 1 forward pass per step. And I think this is crucial because there was no significant difference in generalization. It's just that this is more effective in terms of computation, which is why this is better, and not really why the objective here was to reduce the computation steps and not improve on accuracy is what I meant. The third thing they did was implement exponential moving average. So for small data sets, it's natural for these tiny networks to overfit and then diverge. But by using exponential moving average, uh, they were able to preserve the model accuracy. So on small data, these recursive models, uh, we can smoothen the accuracy out using EMEA. So without it, it was around 79.9%, and with EMA, you can see definitely a improvement. This is simple. This is really a common observation across generative adversarial networks and some diffusion models. And even in paradigms of self-supervised learning, EMA is quite used frequently. This is a simple solution, but in this case, quite essential. Coming to the ablation study, here's the full ablation study table, but I'll make it quick. They tried different variations of TRM. They started with the HRM baseline, and then they moved on to a TRM with 1 step gradient. Then they tried changing their hyperparameters. They Instead of self-attention, they also tried feed-forward. They tried a training without EMEA, the one with 4 layers, and they had different variations of the same network. And what they found out was the best working was when the amount of deep supervision steps were 3 and the inner recursions was 6. And it was effectively simulating a network with 42 layers. Now, let's talk about, before I talk about results, do we have any questions so far?
I don't think so. Yeah.
All right, let's move on to results then.
Yeah.
So, in case of Sudoku Extreme, 9x9 grids, only 1,000 training examples and around 423,000 test examples, which is extreme small sample learning process, right? Every LLM scores is effectively 0. Now, this is again in retrospective. Back when they compared it on the Sudoku Extreme dataset, every single LLM was performing really poorly. And HRM was performing at decent 55% test accuracy, but we can see here TRMs are effectively blowing them out of water. As you can see, since Sudoku Extreme is like a small task, we can actually drop out attention mechanisms and just use normal MLP, and it performs better. Now, talking about maze hard results for 30x30 mazes.
Yeah,
So
so in they won't have trained these LLMs, right? Like they have trained TRM, MLP, and attention. Like they
no,
haven't
no,
trained LLMs, right, for
no, no.
any specific task, but these HRM and TRMs are trained for these tasks.
True. So in case of that, that's a good question. So in case of LLMs, it would be like a in context learning task, right? Where we give it 1,000 samples and then ask it to, and then we test it on a much larger data set. But
Mhm.
it's equivalent to training a small network with only 1,000 samples.
Okay.
Yeah.
So they did in context learning for these LLMs.
Yeah.
Okay.
But now there's an argument over there that it's not really equivalent. But I would say I would beg to differ because these are like huge LLMs with
Yeah.
lots of training and general knowledge, but they are still not able to solve Sudoku puzzles, right?
Yeah. Yeah, you call them as generalist models, so you would at least have some form of accuracy. Zero is very bad.
Exactly.
Yeah.
Yeah, it is
Uh,
surprising.
yeah.
Like 0% accuracy.
To be fair, this was in retrospective, right? Like these are so like older models.
Mm.
I don't have updated results for this, unfortunately, but it would be interesting to see if they have finally catched up.
Mm.
Uh, Again, for maze hard, for like bigger mazes, with shortest paths over 110 steps, again, LLM scores 0 and HRMs score around 75%. Now, in case of maze hard, they have used TRM with attention, and as you can see, it performed really better. It's almost like 10 times improvement with 4 times lesser parameters. And the note that TRM MLP completely fails here. Now that is something I like to highlight, and the reason why that is because for 30 cross 30 mazes, MLP basically fails to attend to every single grid position. It's like it gets overcapacitated because of huge sequence lengths, and it basically shows that the architecture choice matters for each task. Now let's come to the ARC-AGI 1 results. This is a big one. It is 800 geometric puzzle tasks. Each is designed to test the generalization capabilities of the model, and it's quite easy for us humans, but it's difficult for AI, right? The progression, I think, tells a story here, right? So for DeepSeek R1, it was 16%, Claude is 29, and so on. But HRMs are performing quite better as well. And for at least for TRMs, it's 45%. Uh, and this miscellaneous bar, right? Like direct predictions, but this is basically HRM with direct predictions. So think about it like this. Instead of instead of running the recursion and the Q-learning objective, we fine tune it on some tasks of ARC-AGI and ask it to make predictions directly. We're not running recursion steps here. Even in that case, it was able to perform decently as compared to LLMs. But when we do run those halting procedures and everything, we get a much better test time accuracy. And in case of TRMs, TRM beats Gemini 2.5 Pro by around like 8%, I guess, which is a huge leap. As for ARC-AGI 2, which is the newer and harder version of ARC-AGI 1, it has around 1,120 puzzles. Absolute numbers are low across the board. I know like 1% test time accuracy is nothing when it comes to measuring for these benchmarks, but just for comparison, I'm putting these figures here. Even in such low accuracy scores, TRMs are performing, I would say, decent. In my opinion, 8% is nothing when it comes to test time accuracy, and it just shows like we have more room for improvement here. But the David versus Goliath parameter gap is nothing to be ignored of. TRMs are effectively 7 million parameter model, and it's beating a 671 billion parameter model, and that's just shameful. Uh, they also tried training TRMs at different effective depths. So in case of like HRM with 4 layers and a TRM network with 2 layers, what they found out was for k equals 3 and the number of recursion deep supervision steps equals 3, they had the highest level of TRM accuracy, and it was effectively simulating think about it like a network with 42 layers, which is comparable to Kimi K2. I think it has similar amount of layers. So at every match step, TRM outperforms it by around 15 to 20% points on average. Now, what are some key takeaways from both of these works, and what are some lessons, and what are the future directions? So, what didn't work in case of TRMs was replacing the Swiglu's MLPs with mixture of experts. Now, this was interesting because at first thought, we might think that adding the whole mixture of experts might actually improve model accuracy, but that's not necessarily true. By adding unnecessary complexity, we are basically, uh, increasing its complexity, but there is a massive drop in generalization. They also tried backpropagating through only last steps instead of backpropagating through all recursion steps, similar to the fixed point approach. Again, it didn't work. It just added more complexity with no benefits. They tried removing the adaptive computational time, the early halting mechanism, but what they realized is the model just spends more time. It performs 16 recursions for each pass, and that's just not optimal, right? And they tried some architectural changes either, but they didn't work, like trying to tying input embeddings to the output head in order to constrain the weights of output predictions while trading. But the idea was to have like a much more finer way to update the output head. But what ended up happening was there was a massive drop in generalization. Now there are some limitations and future directions for this as well. Architecture choices don't universally transfer, right? MLP fails on large tasks, and there is no theory why recursion actually helps, right? We're assuming that sure we are still getting up to some point, and uh, there is some convergence, and then we do a backpropagation. This is still in its hypothetical stage. We don't have a solid theory around it. Again, this whole training of recursive models is still a supervised task where we have outputs and we compare the predictions with outputs, right? There is no self-supervised learning or unsupervised learning here. We currently don't have any scaling laws, even though papers makes a bold claim that we only need tiny models. We we don't have scaling laws for this. Like how further can we scale these recursive networks? Because if we imagine, let's say for a 20 layer recursion, we will require insane amounts of compute, right? And let's say we're trying to solve a much harder task, even with a smaller network, we still are talking about massive data center grade GPUs running every single day, right? And there is no scaling law for this, but we have a scaling law for LLMs. For as for like future work, they what they expressed was it to extend it to generative tasks. So currently we are doing sequential refinement tasks, right? But it would be interesting to explore generative tasks where we have multiple valid answers, similar to what LLMs do. Uh, and developing the actual scaling laws for recursive networks and getting a theory behind why this recursion works, right? The next interesting aspect is to combine LLMs with TRMs, which is something I was trying to do, but unfortunately, things couldn't work. And unfortunately, I can't give you a demonstration today. But this is a really interesting thing, which I really liked. And the final thing is to test it on more diverse problem domains. Again, finally, just to sum everything up, these are the key takeaways. So deep supervision is actually the secret sauce, where the iterative refinement occurs over multiple steps, which is actually driving the performance. Like when I say this, the ARC-AGI folks, they run ablations on this network, and what they found out was rather than because rather than recursion, the deep supervision is what makes this model great, right? This whole paradigm of iterative refinement. And then second takeaway is tiny networks plus deep recursion outperforms massive LLMs, as we saw. Simpler is better, less is literally more, and we can trade parameters for compute, which is the quite opposite of what the current industry is saying. We need more compute. But yeah, that's all from me. I hope I was able to make this clear. And if you have any questions, we can get them started now.
Thanks, Kaushik. That was
Of
an
course.
amazing presentation.
Yeah.
Finally.
Thanks for the
Yes.
wonderful presentation. Yeah, a lot in-depth knowledge you provided.
Thank you.
with the whole evaluation criteria and stuff. Yeah, wonderful.
Yeah.
Thank you.
Welcome. You're welcome.